I know what you're thinking. Example 11 doesn't even have a logarithm in it. What's it doing in this lesson? Well, bear with me for a minute. We're going to take the derivative of this obnoxious looking function that ordinarily I would have to use both the quotient rule and the chain rule to take its derivative. It would be doable, but kind of tedious, right? Lots of room for error. This time what we're going to do is we're going to take the natural log of both sides. And what that's going to allow me to do over here on the right-hand side is use some properties of logarithms to expand it out and maybe even avoid using the quotient rule. All right, well, let's see. I'm going to take the natural log of both sides. So I'd have the natural log of y is equal to the natural log of this whole big quantity, x minus 2 squared over square root of x squared plus 1. Now notice it says that x cannot be equal to 2 for some reason. Is it obvious why that's the case now? Because if x was equal to 2, I would have 0 up here on the top. 0 divided by, it doesn't even matter. I'd be taking the natural log of 0, which is undefined. All right then, now that that's out of the way, let's now use some properties of exponents over here on the right-hand side and expand this thing out. But first, this gets moved down so I have more room. Bring down the natural log of y, and then I will see if I can do this in one go. This 2 is going to come out of the natural log. This is going to be a difference because I got a quotient, and then the 1/2 power for the square root will also come out. So I have 2 times the natural log of x minus 2 minus 1/2 times the natural log of the x squared plus 1. I almost said square root. Now then, let's take the derivative with respect to x on both sides of this. When we do, we'll have to implicitly differentiate the left side. Why is that? Because you have y inside of the natural log function. It is now an implicit equation. The derivative of the natural log of y is y prime over y. Then I will take the derivative normally on the right-hand side because there's no y's in it. And I am going to, this is u prime over u. The derivative of x minus 2 is just 1. That 2 will be up top. It's going to be 2 over x minus 2. Right? Minus, and then let's do the same kind of thing over here. Let me bring down my 1/2. And the derivative of x squared plus 1 is 2x over, and then the bottom stays the same. Look at that. Let's see how much easier that was than even having to use the quotient rule. I mean, it's not quite done yet, but you're going to see it's still a heck of a lot easier. All right, so I canceled out some stuff with my cancellation crayon. And then what I'm going to do is I don't want y prime over y. I just want y, so I have to multiply this y over here to the other side. So y prime is equal to y times, big old parentheses, 2 over x minus 2 minus x over x squared plus 1. And it's frowned upon generally to leave a y inside of y prime, kind of like taking the second derivative. Whenever you're taking it implicitly, you have to go back and substitute. Well, we're going to go back and substitute what this original function was, which is this guy right there. That's what y is equal to. So y prime is equal to x minus 2 squared over the square root of x squared plus 1 times this new thing that we just found, 2 over x minus 2 minus x over x squared plus 1. Ta-da! Now, is there anything else that you could do with this? Possibly. If there was, it would be like finding a common denominator and then seeing if stuff canceled out. But I'm going to go with this answer right here. It looks pretty good to me. All right. this brings us to this thing, this process that we just did right here. It's got a special name. It's called logarithmic differentiation. Logarithmic differentiation can be beneficial when taking the derivative of complicated products, quotients, or powers. Here it is, step by step. The first step is to take the natural log of both sides of your function, just like what we did. Okay, now that is going to make an implicit equation. So that to take its derivative, you will have to implicitly differentiate. Oh yeah, I'm going to expand using some properties of logarithms. Pretend I said that earlier. Step 2, we're going to differentiate implicitly with respect to x. Anything that has a y, yeah, make sure you have a y prime in there. Anything with an x, you just differentiate normally. And then finally, you have to solve that thing for your dy dx or your y prime. You'll have to probably go back and substitute the original equation back in, just like we had to do when we were taking the second derivative implicitly.